How to implement DFS and BFS on graphs in Haskell. Welcome to video number 2 about graphs in Haskell. Here is how our graph represented. They represent our graph using this structure. This is a list of undirected edges of type A, and we have undirected edge here as a pair, okay, of some type A. And you can see the previous video about this implementation, and here they have a JSON function which takes a graph and some vertex and produce the list of adjacent vertices. Let's start with breadth-first search. How breadth-first search work? Okay, they start from some vertex and then they take all the nearest vertices of this vertex. And so on. For this nearest, they take the other nearest. So the more distant from the starting. And so on. They increase our distance. The main data structure which is used to implement the breadth-first search is queue. So let's write some function which do only one iteration on our breadth-first search. Okay? I will call this function step, and its type signature is, it has some equality type class, the type which I call A, and it has a graph of this type. And next thing, we need to take some pair of our A's. The first list of this pair is our result, and the second list of our pair is our queue. And when we do one iteration, they produce a new state of our algorithm. They produce another result, and they somehow modify our queue. Okay? So actually how this is works. If let's do some helper here. Our step will receive a G and call some helper function. This is G. And the helpers look like this. So it takes some, in some corner case, no matter what is the graph, we take some result, collected result, and our initial queue, and the return, if the queue is empty, they return our state as it is. This means that they can't modify anymore our results, and the iterations can be stopped, our steps can be stopped. But what if we take some graph here and we take some result and some queue here? We will take the head of this queue and also give the tail name queue. Okay, in this case, how we need to modify our state? Okay, of course, we take the head of our queue and put it to our result. like this. And now we need to add to our queue the adjacent vertices of our head. And also we need to remove from these adjacent vertices the vertices what we already visited in our result here, and vertices which are already in our queue. So this means that they need to take this queue and add some adjacent vertices here. So we take our age function, which was implemented in the previous video about graphs. It take adjacent vertices of the graph for our vertex. And they need to, from these adjacent vertices, remove the vertices what we already visited. They subtract them. And also from this result, we need to remove the vertices what that is already in our queue. Okay, and I think this should work. So now we can do some steps of our algorithm. Let's look at this, how it will work. I will load our file here, and let's try to do some step, only one step. We have some graph like looking like this. We can go from A to B, from B to C, from A to C, from X to A, from B to Z, from Z to C. Okay, and now let's take some iteration. And I forgot one thing, of course, here they need to provide our graph G and initial vertex from which we want to start our DFS. And they need to pass from here the initial pair of our state. At this first step, we have the empty visited vertices list, and we start from some queue with only one element from which we start our DFS. Okay. Now let's try to reload this. Sorry, error. Problem is that I need to use this type signature for this function internal step. So let's reload. It's done. And now I can do one step. Okay, let's run this step for our graph G. Let's look at this graph, and we run this step for it, and we start from A. And let's look what we all have. So we have one vertex A visited, and we have B, C, X in our queue. This is because this is the adjacent vertices what we doesn't visit. So A adjacent to B, A adjacent to C here, and A adjacent to X here. Okay. Now, as you guess, I can infinitely many times iterate on this step. So we have function which called iterate. Let's look at its type signature. So we can use our step function in this iterate function. Okay. So let's call our iterate the function step g, and they need to provide some initial state here. So I think I don't need this function here. I'll comment this and we'll use this step function. And here I need to provide some initial state. Okay, let's start from empty. Visited vertices and start from start point. Our initial queue, it's queue with only one element, our starting point A. And now it will give us the iteration process, I think. So let's take some, let's look at this type signature. You can see that they have this list of chars, of pairs of chars that represent our state modification in time. And now we can take the first, for example, 5 elements of these iterations. And you can see here they start to modify our state. So we start from A, then they add B, C, and X. Then they extract B, and it goes to our visited vertices A, B. But B have put Z here, and so on. They extract C to our visited vertices and return ABC, and so on. So if we take 6 iterations, we can see here that they have empty list, empty queue, and this means that they can stop. To stop this, they need to use found function. Find function, and this function they can use it here. As you can see, it takes some foldable as a second argument, and we can use our iterated list here, this list actually, and they need to provide some predicate here. I will use a lambda for this, and pattern match our pair with visited and queue, and I need to stop if okay, of course I need to call find here, and here I need to check that our queue is null. Okay, so in this way we will find our state there we can stop. Okay, let's run, and you can see that we found this last step. Okay, now we can extract it using from just function. Okay, it will always have the result because this algorithm is stopped somehow, and it will stop at some point. Okay, and they extract this from just, and we need to take the first, the visited vertices, and we done. Okay, this is our breadth-first search. Now let's define it as a function BFS which takes some A and of course some graph G, and they put this A here, Okay, and I think we can use this. We can use this to define our function. Okay, let's try to reload. It works. BFS for graph G. We're starting A. We're starting Z. Okay, you can see that this thing works. From Z we can go to B. From B we can go to C and to A. From C to A. Yes, I think this works as expected. But also we can implement the BFS another day. Okay, I will call this BFS2. And let's start from type signature. We have some graph and we have some list of visited vertices A and list of our queue, and they produce our visited vertices. So this BFS can be implemented using recursion. So let's comment this thing, and I'd call also BFS. And we will start from simple corner case. If we have no matter what the graph, no matter what they visited, if our queue is empty, this means that our DFS is empty. Okay. So actually this visited here, that is used to only check that they have already visited our vertices. It doesn't contain their result. So, and what if they have some not empty parameters? So we have some visited here, edges, vertices, and we have some queue, and let's name the top of this queue as head, and we can do the implementation in this way. We can at first extract a head of our queue, and this is the head of our result. Okay, this is the result. These are two vertices. This means that they have this head here, and they need to add this result to the tail of our breadth first search. And of course, the tail of our breadth first search we can construct recursively. So we call our BFS again with our graph G, with our visited vertices. But we need to add, of course, here to our visited vertices, we need to add our head because we already visited here. And also we need to take our queue and add to our queue adjacent vertices minus visited vertices minus vertices what already in our queue. So with the means that they need to call our adjacent function for our graph G and our vertex H, and subtract from these our visited vertices, and also subtract our queue, that vertices that is all already in our queue. So let's put parentheses here. And this is what we add to our queue. Let's check this. And I will try to recompile here this thing. I put some parentheses here. Okay. Sorry, of course I need to concatenate my lists. Reload and be done. And now let's try to run for our graph G, our DFS. G starting from A. I need to provide initial visited vertices is empty list, and we start from A. And we have the result. And I think this is correct result. And now let's do a depth search. Okay. And this is very simple, because to do depth search we need to change only one thing. For breadth search we use a queue, and for depth search we use a stack. This means that we need to change only one thing in this algorithm. So I will rename it DFS, and here how we modify our queue at every step. We add here our adjacent vertices to the end of our queue. But in the case of depth search, they need to add it to the top, like stack. So let's do it. And let's recompile. And now let's try to run our DFS for graph G and vertex A. For DFS, for graph G, we start from the empty visited and from A. Okay, you can see that we have some result. We go from A to B, from B to C, we go deep and deep. From C we go to X, Y, X. From C we can go any more. This is strange. We have X here. Sorry, of course I forgot to change this. So we start DFS and then call BFS. Change it to DFS, and now let's try to again. So AB from B to C, from C A to B, from B we go to Z, we can go from B to Z, then from Z we can go to C, and then we need to go back to our A, and then we can go to X. So it will traverse in this way. And I think this is correct implementation. And also now let's change, let's comment this thing and change it here using our iteration method. So it's work exactly the same. but we need to change our steps. Okay, I will comment this, put this here, and change. I will add this queue here. Okay, and I think this should work. Let's try to recompile and run our DFS. Okay, here I didn't need to provide these lists, just like so, and we can see that this result is ABZCX. ABZCX is exactly the same result using our iteration function. So guys, I think we done the BFS and DFS. Thanks for watching. Push like button, push subscribe button, write comments, and see you in the next video.